So welcome to my homemade home studio. I'd like to start talking about dilution with a demonstration that hopefully is very common sense. So let's say that I have two 1 liter bottles that both have 1 liter of water in them, and I've got some food coloring. We're going to pretend like 3 drops of food coloring is 1 mole of whatever it is. So let's say we're going to put 1 mole in each one of these 1 liter bottles. So 1, 2, 3, 1, 2, 3. So now the molarity, once it gets stirred up a bit, so let's mix this in our vortex providing way. Go like this and you turn it into a little tornado. So now each one of these bottles is a 1 molar solution. 1 mole of food coloring for 1 liter of solution. So they've got the same molarity, same concentration, and I'm going to put one of them into this 2 liter bottle. So the concentrations of these two are equal, right? 1 mole in 1 liter, 1 mole in 1 liter. 3 drops of food coloring, 3 drops of food coloring. But what if I dilute this? What if I put 1 more liter of water in there? So now, what's the same and what's different? There are still 3 drops of food coloring in the one on the left, right? The number of moles is the same in the 2 liter bottle. But there's twice as much liters. There's twice, the volume is twice as big. So now the molarity of this is no longer 1 mole per liter, it's 1 mole per 2 liters, which is a 0.5 molar solution. So this is a 1 molar solution, 1 mole in 1 liter. This is a 0.5 molar solution, 1 mole in 2 liters. The thing that's the same about these two is the number of moles. But the volume is different, 2 liters and 1 liter, and the concentration is different, 1 molar and 0.5 molars. The central theme for doing the calculations in molarity problems and dilutions is that the number of moles is the same before and after the dilution. Let's do some calculations to figure out how to do these problems. So let's take a look at how to do these notes, how to do the calculations with dilutions. So notes, dilution calculation. And what we just saw in the demo is that if you have 1 liter of a solution and you have 1 mole, and let's say we're talking about sodium chloride. So let's say that green food coloring was really sodium chloride. You had 1 mole of sodium chloride, let's say, so you made some salt water. If you have 1 mole in 1 liter, then you can say that molarity is number of moles of solute, which is like the salt, divided by liters of solution. So we had 1 mole per liter, or 1 molar NaCl. But then we diluted it. So we took that, and instead of it being 1 liter, we put it into 2 liters. Now it was still 1 mole of NaCl, well, food coloring. So now we can say that the molarity is 1 mole still, but it's in 2 liters. So we've diluted it, and the new molarity is 0.5 molar NaCl. The thing that was the same before and after is the number of moles. So that's the principle. can leave it like that. So the principle of dilutions, is that the volume changes, the concentration changes, but the number of moles stays the same. And that gives us a basis for figuring out a formula. This is tricky. See if you like this. So here's the derivation. We know that molarity equals moles of solute per liter of solution. And if we just want to rearrange these equations, or to rearrange a little bit with algebra trick, I multiply both sides by liters. I can say that moles, number of moles, equals molarity times liter, right? Because I just multiply liter by both sides. And I know that the number of moles before the dilution, when I just had my 1 molar solution, equals the number of moles after. And in the Canvas model, they said that before was the stock solution. So before, they said, was S, and then the after was the diluted solution, so they said D. So we can say that the moles of the stock solution equals the moles of the diluted solution, just like with our green food coloring. Well, if we know that, or if we're willing to say that moles is molarity times liters, we could say that the moles of the stock is the same as the molarity of the solution times the liters of the solution. So I'm just substituting that there, and that equals the molarity of the diluted times the liter of the diluted. But it turns out that it works for liters, but if we wanted this to be milliliters instead, the way to go from liters to milliliters is times 1,000, right? So that I could do times 1,000 on each side, and it would be molarity times the milliliters. Or if I wanted to change it to teaspoons or gallons or anything, whatever I did to the left, I'd do to the right. So instead of saying that it has to be liters, we can say it works for any volume. So we'll say the molarity of the stock solution times the volume of the stock solution before equals the molarity of the diluted solution times the volume of the diluted solution. That's the after. And again, your volumes can be anything as long as they agree. They have to have the same units. So if this is milliliters, that has to be milliliters. If this is gallons, that has to be gallons. All right, so let's do a problem with this. So here's some sample problems. What if you add 105 milliliters of water to 250 milliliters of a 3.97 molar hydrochloric acid? What's the molarity of the new solution? So you're diluting it. So we're going to say MSVS equals MDVD. That's the formula we'll be using. And the key for these is figuring out what means what. So I'm going to list these. This is to help us out, and I suggest that you do this every single time you do one of these. I would not think of doing these without listing it out, and I've done this for years. So we look at this and we say the molarity of the stock was 3.97 molar. 3.97 molar. The volume of the stock was 250 milliliters. I don't have to change it to liters. Says, what's the molarity, so this is what we're looking for, of the new solution. Now, let's be careful for a minute there. What's the volume of the diluted solution? It's not 250, that's what it started out with. It's not 105 milliliters, because that's just the water. We have to add these together to get the new volume. So 105 milliliters of water plus 250 milliliters of the stock solution will give us our new volume. And that's going to be 355 milliliters. So you have to be on your feet. You have to be thinking while you're doing this. And then we're going to solve for the molarity of the diluted thing. So I'm going to rearrange this a little bit just because I think it makes it easier. The molarity of the diluted is going to equal MSVS divided by the volume of the new stuff, of the diluted stuff, VD. So I just rearranged this to make it fit what I want it to be. So the molarity of the diluted thing is going to be 3.97 molar times 250 milliliter divided by the new volume, which is 355 milliliters. And you'll notice that the milliliters will cancel out and we'll be leaving just molarity as our units, which is what we want. So you get your calculator out, and to give that 3 sig figs, you can try it, but it's 2.80 molar. So the molarity of the new diluted stuff is 2.80 molar. Let's try another one. So you have 5 liters of a 3 molar nitric acid solution and you add it to 2 liters of water. What will be the new molarity? So once again, we're going to say MSBS equals MDVD. And we want to list these all out every single time. We're starting out with 5 liters, 5.00 liters, of the 3 molar nitric acid solution. We want to find the new molarity, and we added it to 2 liters of water. So the final volume is going to be those 2 liters of water we put in and the 5.00 liters, so a total of 7.00 liters is our new solution. So once again, we can rearrange this. So the molarity of the diluted thing is going to be MSVS divided by the volume of the final diluted solution. So we have 3.00 molar times 5.00 liters divided by 7.00 liters. And you work this through on your calculator and you'll get 2.14 molar for the molarity of the diluted solution. So here's another one. Let's say you've got the question of how much water do you need to add. All right, so this is a little bit tricky. So let's say you have how much water must you add to 300 milliliters of a 6 molar sodium hydroxide solution to make it a 1.50 molar solution. This is actually really practical, but we still use the MSVS equals MDVD, and we're going to list them out. And we have to figure everything out. Okay, so we're starting out with 300 milliliters of the concentrated stuff. So 300 milliliters of the concentrated sodium hydroxide, which has a very scary concentration of 6.00 molar. Don't get that in your eye, please. But the goal is to make it a 1.50 molar solution. So that's going to be the molarity of the diluted stuff. So 1.50 molar. Now, to figure out what the volume is of the water that has to be added, let's find the volume of the final solution first. And then we can subtract off the volume of the original that was put in there. So to figure out how much water you need to put in, let's figure out the total volume and subtract off the volume of the stock solution. So now we're going to say that VD, so I'm going to solve for VD, is MSVS over MD. So I'm going to be solving for the one thing we don't know here. So that'll be 6.00 molar times 300 milliliters. And notice it's really a good idea to put the units in, because then when everything cancels out, 1.50 molar, you get confirmation that you're doing it right, because our final answer will be in milliliters. So that'll be the final volume of all that. So you work that through, and you end up with 1,200 milliliters. So that's the volume of that one. Now I only have 3 sig figs, so 1,200 with a bar there. That's the total volume that gets made. But you started out with 300 milliliters. So if you subtract off 300 milliliters of the stock, so this is diluted, subtract off the 300 milliliters of the stock solution, and you'll end up with 900 milliliters of water that was added. Now what about sig figs? Okay, this is kind of an annoying sig fig kind of thing, because this was only accurate to the tens place. So that means that our final answer can only be accurate to the tens place. So we only get 2 sig figs for the final answer on that one. That's a technicality, don't worry, that won't be on the test or anything, but those of you who are sig figs savvy, you say, well, of course, that's the way it is. All right, last one. This question is, how many milliliters of a 4 molar phosphoric acid solution are needed to prepare 125 milliliters of a 3.05 molar solution? You look at that and you usually, most brains just sort of say, don't know what to do, but writing this out first before you even try to understand it makes it all easy. You break up the question into small pieces and do all the small pieces. That's the engineering way. Break up your big problem into small problems and solve each of the small problems. All right, so we're starting out. We're looking for how many milliliters of this solution. So we're looking for the volume of the stock solution. And we know the stock solution is 4.00 molar. And we want to make, for the diluted stuff, we want the volume to be 125 milliliters. And we want it to be 3.05 molar. So now it looks easy. Just solve for VS, and you don't even have to do any fancy stuff with water at the end. So the VS, volume of the stock solution, is going to be MdVd divided by the molarity of the stock stuff. And now we just plug in the numbers. So 3.05 molar times 125 milliliter divided by 4.00 molar. So I'm just following the script. So you work this through on your calculator and you end up with 95.3 milliliters is the volume of the stock that you would need to add to make 125 milliliters of the diluted stuff. And you could figure out how much water had to be added by subtracting those two if you wanted to. So remember, the basis of this is that the moles before the dilution equal the moles after the dilution. And we just did a little bit of algebra trickery to get the moles before to have a nice little equation and the moles after to have a nice little equation, so we can solve for the one that's missing, the one term that's missing of the 4 terms. Enjoy your day.